So we'll continue with the exercises. We are now in problem 4a. So let H1 rad Rn be set of all u in H1 of Rn, u radial. That means u of x is just a function of mod x. It depends only on mod x. Okay. So if u belongs to H1 rad Rn, show that there exists un in D of Rn radial such that un goes to u in H1 of Rn. The norm is still the same. This is only a subspace and therefore you have this. So solution. So we know that zeta m rho m star u belongs to D of Rn. Zeta is the usual function, support of zeta in ball of radius 2. Zeta is identically 1 in a radius of 1, 0 less than or equal to zeta less than or equal to 1. Zeta m is zeta of x by m. Okay, so this is the usual standard thing, and zeta m rho m star u converges to u in H1 of Rn. So we can take zeta radial, hence zeta m is radial. Also rho m is radial. So enough to show that the convolution of two radial functions is radial. So because rho m star u will be radial, you are multiplying by another radial function, so everything will be radial, and that converges, and that's in D of Rn, and therefore the whole thing will be true. Okay, so Fg radial, okay, and T from Rn to Rn rotation. What is radial? Radial means it should be the same when you do any rotation. Okay, so f star g of Tx is equal to integral over Rn f of Tx minus y g of y dy. Okay. So you write y equal to t times z because t is a rotation and mod determinant t will be equal to 1, and therefore you have this will be integral over Rn by the change of variable formula f of t of x minus z g of tz dz. And that because f and g are now radial, so this is equal to integral Rn f of x minus z g of z dz, since fg radial, and that's equal to f star g of x. And therefore for every rotation you have this, so this implies that f star g is radial. Okay, so B, let u in D of Rn be radial. Using r power n minus 1 mod ur square equals minus integral r to infinity d by ds s power n minus 1 us square ds show that for all x in Rn, you have u of x in absolute value is less than or equal to 2 by alpha n power half mod x power minus of n minus 1 by 2 mod u power half 1 Rn mod u 0 of Rn. Alpha n equals surface measure of unit sphere in Rn. Deduce star for almost every x in Rn when u belongs to H1 rad Rn. So this is star. So u is in d of Rn radial, and you have r power n minus 1 mod ur square equals minus integral r to infinity d by ds s power n minus 1 mod us square ds, because this is just a integral of a derivative and therefore it's minus n values. U is in d of Rn, so at infinity will give you nothing. With a minus sign you get exactly the lower limit, and that is equal to that. So that is equal to minus integral over r. So I am going to just differentiate that. So n minus 1 s to the n minus 2 mod us square ds, so integral r to infinity minus 2 times integral r to infinity s to the n minus 1 u of s u dash of s ds. Now this integrand is non-negative, okay. Everything is between r to infinity, everything is non-negative, and therefore the integral will be non-negative, and consequently you have r power n minus 1 mod ur square is less than or equal to minus 2 integral r to infinity s to the n minus 1 us u dash s ds. Now if I had an alpha n here, so let me put an alpha n. Now if I put an alpha n s power n minus 1 into a function like this is nothing but the integral of the radial function. So this is equal to minus 2 by alpha n integral mod x greater than or equal to r, okay, u du by dr dx. This is just polar coordinates, the integration of a radial function, and therefore 2ab, so that is by the Cauchy-Schwarz inequality, less than or equal to 2 by alpha n mod u 0. In this domain I can say less than or equal to 0 Rn mod u 1 Rn, because again u radial, du by dr modulus of that will give you modulus of the gradient also. So and therefore the inequality now follows, because you just take, so inequality follows. R equals mod x. So if you just put that, then inequality star follows. So if u is in H1 rad Rn, then you have un in d of Rn radial and un converging to u in H1 of Rn implies star true by density. And also since un goes to u, unx goes to u of x almost everywhere for a subsequence. Okay, so hence this result follows. C. Let 2 less than q less than 2 star, which is 2n by n minus 2. Let un converge to 0 in h1 of Rn weak. Un in h1 rad Rn will then imply that un goes to 0 in LQ of R. So this, then okay, so this is what, so thus you have h1 rad Rn in LQ of Rn is compact. So you see, this is a case, even though Rn is an unbounded domain and in general you don't have a Lick theorem, if you reduce it to radial functions, then it becomes a compact thing, because radial function means it essentially depends only in one dimension, and therefore so if you have radial functions, then if you restrict your attention, then h1 radial Rn in LQ becomes compact. So this is a nice observation. So let us take solution. So 2 less than q less than 2 star. Okay, so you take integral over Rn mod unq dx, that's equal to integral mod x less than or equal to some r which we will choose, okay, mod unq dx plus integral mod x greater than r mod unq dx. So let us take mod x greater than r, and you have q is bigger than 2, therefore mod un to the q minus 2. Okay, so this I will write as integral mod x less than or equal to r mod unq dx plus integral mod x greater than r mod un q minus 2 mod u power q un power q dx. Sorry, not q, 2. So mod un 2 minus q is less than or equal to by star. So we are using the inequality star. This is almost every x. So this you have less than or equal to 2 by alpha n to the power of q minus 2 by 2 into 1 over capital R. Okay, mod x is bigger than r, so you are in the denominator, so this is less than r power n minus 1 by 2 into q minus 2. And then you have mod u q minus 2 by 2 0 Rn mod un q minus 2 by 2 1 Rn, which is less than or equal to, so mod un it converges weakly, so it is bounded in h1 of Rn, and therefore this will be less than c. It's in L2 norm will also be less than or equal to c. This all this stuff I am going to put it in one thing. So this is less than c divided by r to the power of n minus 1 by 2 into q minus 2. So integral on Rn mod un to the q dx is less than or equal to integral mod x less than or equal to r mod un q dx plus c by r to the n minus 1 by 2 into q minus 2. So q is okay, so we are having all that, and then integral over Rn, I can say mod un square dx, and again this is bounded by some constant because un is bounded in H1 and therefore in L2 also. Okay. Now B0R is a bounded set. So choose R large enough such that second integral on RHS is less than epsilon by 2. Now B0R is a bounded set. So un goes to 0 weakly in H1 of Rn, that's what is given, right, in H1 of Rn, and therefore it will go, implies un goes to 0 weakly in H1 of B0R also. It's true for anything because that is contained in the other one, and okay, and therefore you have that un goes to 0 in LQ of B0R. So choose n such that first integral on RHS is less than epsilon by 2. So this implies integral over Rn mod unq dx is less than epsilon for all n greater or equal to capital N, and that is un goes to 0 in LQ. Okay, so this will not work for q equal to 2 because you have a q minus 2 factor here, and if you want r this integral this to be made small, this term, and therefore you will need that q is bigger than 2, so it won't work for q equal to 2. So that is the part D of this exercise. So u in H1 rad Rn 0 such that mod u 0 Rn equal to 1, okay, and you define uk of x equals k power minus n by 2 u of x over k. Then show that mod uk 1 Rn goes to 0 and mod uk 0 Rn equal to 1 for all k, and that will imply that H1 rad Rn in L2 of Rn is not compact, because this uk will go weakly to 0 in H1 rad, but then it will not go in L2 rad because its norm is completely 1. Okay, so solution. So integral on Rn mod grad uk square equals k power minus n of integral Rn. So I am going to differentiate, so that I will get 1 by k square mod grad u x by k square dx. So dx k power minus n, if you put x by k equal to y, this will give you 1 by k square integral Rn mod grad uy square dy, and that goes to 0 as k tends to infinity, and integral over Rn mod uk square dx equals integral over Rn k power minus n mod u x by k square dy dx, and that's equal to integral over Rn mod u y square dy, and that's equal to 1. Okay. So now if u is radial, this implies uk is also radial, and uk is bounded in H1 of Rn, because its one norm goes to 0 and the L2 norm is constant. So this is bounded. So implies there exists weakly convergent subsequence. So UK converges to U weakly in H1 of Rn. Assume UK converges to assume H1 rad Rn into L2 rad, L2 of Rn is compact. So this will imply that UK converges to U in L2 of Rn implies mod U 0 Rn equal to 1. Okay, and UK converges to U pointwise almost everywhere for a subsequence. But by star, since UK 1 Rn goes to 0, we have mod UK of x goes to 0, and this implies that u of x equal to 0 almost everywhere, and that's a contradiction, because u is 0 almost everywhere, mod u 0 Rn is equal to 1, and that is not possible. So you have that in even the L2 thing and L2 star, both of them are not compact. Let S equal to n by 2 plus alpha, 0 less than alpha less than 1. So delta x equals Dirac distribution concentrated at x. Show that norm delta x minus delta y minus s Rn is less than or equal to Cn times mod x minus y to the alpha. Deduce that almost every xy in Rn you have, and u is in hs of Rn, we have mod ux minus uy is less than or equal to Cn C alpha. So this is C alpha mod x minus y to the alpha norm u 1 Rn S Rn, sorry. So this tells you that norm u s Rn. Okay, so this tells you that it is Helder continuity. So this is a different proof of the Helder continuity of Hs. We know that if S is bigger than n by 2, delta x, Dirac distribution belongs to Hf minus s. Okay, so solution, you have norm delta x minus delta y minus s Rn whole square is equal to integral on Rn of 1 plus mod xi square to the minus s into mod. So we have e power minus 2 pi i xi minus e power minus 2 pi I y dot psi square dz. Why is this? Because delta x hat phi equals delta x of phi hat, and that's equal to phi hat of x, and that's equal to e power minus 2 pi I x dot psi phi x phi psi d psi, and therefore you have that delta x hat is nothing but this expression here. Okay, so this is how we have already seen this before. Okay, fine. Okay, so now we will say this is less than or equal to integral over mod xi less than or equal to r and plus integral mod xi greater than r. So we will split it into two parts. So mod xi less than or equal to r, okay, we will assume, we will prove mean value theorem implies mod e power minus 2 pi I x dot psi minus e power minus 2 pi I y dot psi square is less than or equal to 4 pi square. So I just take the derivative into mod x minus y square into mod psi square. It's just a mean value term. And if mod psi is bigger than r, then we will have e power minus 2 pi I x dot psi minus e power minus 2 pi I y dot psi. We will simply take each one is of modulus 1, so the sum is less than modulus 2, so square will be less than or equal to 4. Okay. So we have norm delta x minus delta y square minus s Rn is less than or equal to 4 pi square mod x minus y square integral mod xi less than or equal to r of mod xi square by 1 plus mod xi square to the power of s d psi plus 4 times integral mod xi bigger than r of d psi by 1 plus mod xi square power s. Which is equal to 4 pi square mod x minus y square, and then I am going to write it in terms of in polar coordinates. So this is equal to 0 to r of r power n minus 1, you will get alpha n, and then there is already r square here, so you get r power n plus 1 dr by 1 plus r square power s. Plus 4 alpha n integral r to infinity r power n minus 1 by 1 plus r square to the s. And remember, s is equal to n by 2 plus alpha. Which is less than or equal to 4 pi square mod x minus y square alpha n integral 0 to r power n plus 1, and then 1 plus r square is greater than or equal to r square, so it's in denominator, so it's less than r square, so r power 2s, which is r power n plus 2 alpha dr plus 4 alpha n integral r to infinity. The same thing we will do, we will have the r power n minus 1 by r power n plus 2 alpha. Now 0 less than alpha is less than 1, so this implies that 1 minus 2 alpha is bigger than minus 1. So norm delta x minus delta y square minus s Rn is less than or equal to 4 alpha n, I will take it out as a common factor. So you get pi square mod x minus y square by 2 minus 2 alpha into r to the power of 2 minus 2 alpha plus 1 by 2 alpha r power minus 2 alpha. Okay. Now choose r equals mod x minus y to the minus 1. Okay, we can choose r, so now we choose, then you get norm delta x minus delta y square minus s Rn is less or equal to some c alpha times, so you get mod x minus y to the 2 alpha. Okay. Okay. So now if u is in Hs of Rn, then mod ux minus uy is nothing but delta x minus delta y acting on u and modulus of that. So this is equal to norm of delta x minus delta y minus s Rn norm u s Rn, and therefore that gives you, that's less than equal to c alpha times mod x minus y square to the alpha. Okay, and norm u yes r. So with this we complete the exercises for this chapter and this chapter also. So next time we will take up weak solutions of elliptic boundary value problems.